Hi everybody, welcome to another video in Calculus 3. We still not get to calculus yet, we still review with calculus. Right, cross products. So just go over the definition first. Given two non-zero vector u and v in R3 three-dimensional space, the cross product is a vector with magnitude equal to that, and theta is the angle between the two vectors. Direction is given by the right hand rule. So that is a lot different than the definition of the dot product. Right. So I have the definition of the dot product earlier. So let's find how many or the difference between the two. That's a lot. So first of all, in the definition, given two non-zero vectors that are the same, u and v, in the dot product doesn't matter the dimension, but in the cross product it has to be in R3. So those little things are really important. The cross product is a vector that is also important, whereas we say the dot product is a scalar. Sometimes the dot product is referred to as a scalar product, but we're talking about cross product here, which is a vector, and the magnitude is defined by the product of the magnitudes times sine of theta, and theta is the angle between them, and the direction of u cross v is given by the right hand rule. So because it is the vector, it will have a direction. Right. So the right hand rule, how does it work? So we talk about this. So I have to turn the page now. We put the fingers into the first vector and then curve it into the direction of the second vector. The thumb will determine the direction of the product. So this is coming up. So first vector and then curve the fingers into the second. The thumb will determine the direction. Right, now what else do we have about? Right, in here we say cosine is even. So in that case we just have the angle between two vectors. Now, but this one is a little different here. So theta is the angle between u and v, but it is not between u and v. Remember, sine is not like cosine. Sine is an odd function. Sine is odd, so then I need to write that somewhere. Sine is odd. That means sine of a negative angle is a negative of sine of that angle. So in this case, when we have two vectors, the angle from u and v and the angle from v to u, from u to v are different, opposite direction. Therefore, it will be opposite. So in this case, if we want to be precise, the angle is not between u and v, the angle from u to v. Be more precise. So you see, angle from u to v, and if we curl the finger in that direction, the thumb will give us the direction of the cross product. So there's a lot of things. In three dimensions, it is a vector. Because it's a vector, it has the direction, and the angle of the vectors are important. We can, from u to v is different than from v to u, so have to pay attention on that too. Right, so now let u and v be two non-zero vector in R3, right? The vector u and v are parallel if and only if the cross product equal to 0, and that makes sense because sine of 0 degree or sine of 180 degrees is equal to 0, right? Whether we have 0 degree or pi, sine of theta is going to be 0. So that's why the cross product is equal to 0. Now, if u and v are two sides of parallelogram, then the area of the parallelogram given by the magnitude of the cross product. So we have that. And the derived formula is very simple. Base times height, and then the height is v times the angle between them. So pretty much that. That's very simple. Right. Now the properties of the cross product. U cross V is opposite of V cross U. That makes sense. Because if we go from U to V, and then from V to U, the angle will be opposite. If the angle is opposite, the sign will be opposite. Therefore, the cross product will be opposite. Product of U and V is still the same though. Right? So, right, the angle between U and V, the sign is going to be opposite, so that's why there's a negative. And the other properties is pretty standard. Right. Now, find the magnitudes and direction of U cross V for that. So right now we only have the definition. The magnitudes of U cross V is equal to the product of the magnitude times sine of the angle in between them. Right. So let's just find of course we just find the angle between them, because we do need the direction as well. Right. We can draw it out, or we can just find the angle between two vectors. That will be easy. By the way, the vector U is in the xy plane and V is in three-dimensional space. Right. Yeah, let's just find the angle between two vectors, right? Right. So, angle between two vectors, it is easy to use. It's dot product of U over V, U and V over the products of magnitude. So 1, 1 and 0, dot 1, 1 and square root of 2 over 1 square plus 1 square, 0 square, 1 square plus 1 square plus square root of 2 square. So it's 1 and 1, 0 times square of 2, 0. So, and then at the bottom we have square root of 2, and 1, 1, and 2, so it's 4. So we have 2 over 2 square root of 2. Cancel out, we just have 1 over square root of 2. By the way, that's like square root of 2 over 2. So in that case, cosine, I don't even need calculator for this. Cosine inverse, 45 degrees. So the angle between two vectors, 45 degrees. By the way, I did say the angle between two vectors, so it doesn't matter if it is from U to V or from V to U. Right. So the magnitude, though, that's what we focus here, right? The magnitude of U, that is U, so the magnitude is going to be 1 square plus 1 square plus 0 square, Pythagorean theorem. And then that 1 square plus 1 square plus square root of 2 square, and then sine of 45 degrees. And we have square root of 2, and then square root of 4, which is 2, and sine of 45 degrees. So 2 square root of 2, and sine 45 square of 2 over 2. Alright, there's a lot to simplify. Square of 2 is square root of, 2 and 2 cancel out. Square of 2 times square root of 2 is 2. So the magnitude is 2. And the direction, though, determine that in a minute. But, okay, let's just try to sketch. So first we have 1, 1 and 0, so more like this is the vector u. And vector v is still 1, 1, but we go up square root of 2. And now, so the right hand rule from u to v, right hand rule, so we will have that which is, this is the direction of the cross product. Kind of difficult to describe that here, but right, we go from 1, put angle on u, and then curl v, and then the direction will be here. So the thumb will be this, and the finger curling around like that. Right. Find the magnitudes and the direction of v and u. So the magnitudes of v cross u is still the same thing though, because the 45 is the angle between them. So we're still doing that, and we should be able to get the same thing as 2. However, the difference between the u cross v and v cross u is just the direction. U cross v, we point in the opposite direction. Right. So when we change the direction of u and v, we will change the, change the order of u and v. We change the direction of the cross product. Right. That should be right. Now, cross product coordinates define what is the cross product of I and I, vector component I and I. To recall, component I is 1, 0, 0, j, 0, 1 and 0, and k, 0, 0 and 1. Right. So the cross product of I and I, that easy, is going to be right. So later on we'll define the cross product, but for now, if we talk about the magnitudes of the cross product of I cross I is the magnitudes of I times the magnitude of I times the sine of the angle in between them. The magnitudes of this, because it's easy, square root of 1 square, 0 square plus 0 square. And then sine of I and I, so 0 degree. Sine of 0 degree is 0, so it doesn't matter what it is equal to 0. So because the magnitude equal to 0, we can say this is a 0 vector. Next, I cross j. Let's just write I cross j. Later on there will be a much better way to do this, but for now let's look at the magnitudes of the cross product. I j, and then the angle between them. Right, because the magnitudes of I and then j, both of them are 1 though. And sine, we know it's 90 degrees because I is in the x direction, y in the j direction. J in the y direction. So direction of I into j. And remember, the right hand rule from I to j is the angle, is the direction of the finger curling, right, from x to y. So yes, so this is sine of 90 degree. So 1 times 1 times 90 degree is positive 1. and the direction determined that is pointing up, so it's going to be, because the magnitude of 1 that pointing straight up, we can define that to, we can say that is equal to k. Now how about I cross k? 1 0 and 0, cross 0 1 and 0. Right. Now we talk about the magnitude. Right. Just want to go back to this. Even though in here, remember this is the magnitude, right? Sine, even though it is opposite, like the angle is going to be opposite like that, so there will be a difference in that. But if we talk about the magnitude, so definition is still fine. If we just talk about the magnitude, so it's still in between. Why is that? Yeah, because if sine and we put a negative angle in here, if we put a negative angle in here, that would be negative. So in that case, the angle is whatever it is, just make it that show that it is a positive angle. So yeah, the angle from U to V is to determine the direction, yes, but in terms of the magnitude, not trying to confuse you, but in terms of magnitude, whatever angle here have to be positive. So yes, so this is exactly like that. The angle sometimes from U to V or from V to U, that just to determine the direction. But in terms of magnitude, remember, the angle here have to be positive. Magnitude cannot be negative. So earlier I said that from U to V, but like I said, if we want the magnitude, it have to be positive. So don't do that. Yeah, just put a positive angle in there. That should be fine. But in terms of the angle though, is angle from U to V and from V to U actually make a difference in terms using sine. Yeah, so cosine doesn't matter, but for sine we have to make sure that what we put in the formula have to be positive. Right. I is that, so it will be 1 square, 0 square, 0 square, 0 square, 0 square, 1 square, and sine. Alright, I and k, this angle is 90 degrees. Like I said, only put the negative angle here. It would be wrong if we put the negative angle, because magnitude cannot be negative. So we have 1 times sine of 90 degrees, which is 1. So it's 1. So the magnitude is 1, but the direction is different though. Oh, I'm not talking about that. Between I and K, right? Sorry. Angle I and K. Talking about this angle. Now, if the angle between them is easy, remember this is when we do the determine the direction, it's important that we have to be angle theta is from I to K, so it's curling that, so the product is actually pointing that direction, and the magnitude is equal to 1, so this is negative J. Once again, the magnitude is 1, but it points opposite direction as the positive y-axis, so that is negative J. When I'm talking about the angle from U to V is different angle from V to U, I'm talking about the direction. From U to V, the term will determine the direction, because when we switch that, right? So in cosine it doesn't matter, we can put the positive or negative angle, it doesn't matter. But in sine we can only put the positive angle there. Yeah. So in here it doesn't matter, we can even put the negative angle, it's still perfectly fine. Besides, another thing, in the dot product there's no magnitudes here, right? But the definition we have for the cross product, there is the magnitudes. So this guaranteed to be positive. If it is positive, the angle have to be positive. For dot product, doesn't have to be positive. The angle could be negative. It doesn't matter. So this condition here is not really important. Right. Now, so we get back to this. I cross I is equal to 0 vector. I cross j is equal to k. I cross k is equal to negative j. So actually it's easy to determine. Go by a cyclic relation like this. I cross j is equal to k, j cross k is equal to I, and k cross I equal to j. So that is this direction. If we have to go backward, j cross I is equal to negative k, k cross j is negative I, and so on. So I, j, and k in that direction. If we go backward, if we switch because we just switched the direction. Right. Yeah. Before we go any further, I said the magnitudes of the cross product, whatever angle here, have to be positive. Yeah. But in the dot product, the angle, we can just put the negative in. It doesn't matter. Right. Now, luckily we don't have to use this to find the cross product. We have the better way. So this is the 3x3 determinant. So what do we do here? So first, we're going to cover the first row of I, j, and k. We're going to write out I, j, and k. It's going to be positive, negative, and positive. So there's a minus here too. So that is the 3x3 determinant. After that, we're going to cover the column of I. We have U2, U3, V2, V3. And column the J, cover the J, U1, U3, V1, V3. And cover the K, U1, U2, V2, V1, V2. Right, for the 2x2 determinants, it's going to be U2, V3 minus U3, V2, direction I minus U1, V3, U3, V1, J plus U1, V2, U2, V1 in K. Right, simple enough. So we just do that. Now it would be much better if we just use that. By the way, 3x3 determinants, there are a bunch of different ways to do the 3x3 determinants. But we stick it doing the cross product, the 3x3 determinant this way, right? Which is called the cofactor expansion. But anyway, that's not very important. Right. So what we do is we put the vector u first and v. So it's very important. The cross product of u and v is opposite to v cross u. So when we put in the rows, the first vectors and the second vectors put in the row. So now u cross v. The first vectors is the ijk component. And then the first vector is u, 1, 1, and 0. The second vector is 1, negative 2, and 3. So first we cover the vector I. We have 1, 0, -2, and 3. And then remember for j it is negative. We have 1, 0, 1, and 3. And then back to plus. This is j. And then for k, 1, 1, 1, -2. So 2 by 2 determinant, 1 times 3, 3 minus 0, so 3i minus 1 times 3, 3, but with the minus, so it's minus 3j, and minus 2 minus 1, so minus 3k. So we can just say 3, -3, and -3. So vector just like that. So usually we talk about the direction. It's not really important. If we can give a vector like this, it's even better. Right. Find a vector that is normal or orthogonal to both. Right. One thing we haven't mentioned before. Right. So in terms of the cross product, we determine using the right-hand rule. Actually, it is in the picture. I just didn't mention it. So the dimension of the cross, when with the direction of the cross product, is the third dimension, and actually that is perpendicular to both. So cross product is perpendicular to the plane containing the 2 points. It is say anywhere. No. The direction is determined by the right-hand rule, but we say u cross v is orthogonal to the plane containing u and v, or we just say orthogonal to both u and v. So that is the direction. It is orthogonal to both u and v. Right. So we know how to do the cross product. Now, if we want that is normal or orthonormal to two vectors, that means we just do the cross product. That will do it. So it's easy. We just take u cross v pretty much. Use cross v step I, j, k, -1 for I, 0 for j, and 6 for k, 2 for I, -3 for j, and 1 for k. Right, just do like that. For I, cross that out. 0 and 6, -3 and 1 in I, minus -1, 6, 2 and 1, j, and then back to plus, -1, 0, 2 and -3, k. So we do that. That should be easy. 0 times 1 is 0. For 1, I just 0 times 1 minus 6 times -3 in direction of I, minus 1 times 1 minus 6 times 2 direction of j, plus -1 times -3 minus 0 times 2 direction of k. So we do that. So negative that 18i and -1 minus 12 minus 13 with a not a minus plus 13j and then -1 -3, so it's 3k, 18, 13, and then 3. Right, simple enough. That's a cross product, right? Now, so what did we know about the cross product so far? Given the magnitudes of the cross product is equal to that where sine is an angle in between, just make sure that whatever the angle in between have to be positive. Otherwise, the magnitudes cannot be negative. Or the magnitude equal to something negative would be wrong. So the angle here must be positive. We know the direction is orthogonal to both of them. Furthermore, we can say that if u and v are two sides of the parallelogram, then the magnitudes of the cross product give us the area of the parallelogram. So this is very important. It's given by that. Right. Now, we have an example. I'll find the area of a triangle OPQ. Now, OPQ, and let's say this is another point. This will form a parallelogram. So the area of a triangle is half of that. So that's exactly what we have here. Area of the parallelogram is going to be equal to OP cross OQ. Area of a triangle will be half of that. So just half of a cross product. But first, we need to find OP and OQ. OP is P minus O. P 2, 3, 4. That is not 0, that is the point O, which is 0, 0, 0. Now when we write the final thing, we're going to put that in the vector notation with the bracket. I mean, in high level, we just ignore it, we just write the parentheses on the way. Right, OQ, Q minus O. 3, 2, 0, minus 0, 0, 0. 3, 2, and 0. Right. Notice that in the parallelogram, when we find the area, it have to be adjacent. We cannot just take this vector. Let's say when we cross with this vector, that will not work. Remember, the vector have to be adjacent. And certainly you cannot cross the parallel vectors. The cross product of parallel vector is going to be a 0 vector, right? Think about this. If we have two vectors, then we can have an angle in between them. We can determine the third direction using the right hand rule. If both of them are the same, we really don't have an angle to turn. So we don't know if we turn this way, or we turn this way, or we turn that way. So because it point in every direction, the only case it works is the magnitude equal to 0. So in that case, if we cannot take parallel vectors and do the cross product, because that's going to give us 0, will not give us the area of the parallelogram. Besides, the magnitude is the cross product is equal to that, and if sine of 0 degree or of 180 degrees is 0, and the magnitude would be 0, so cannot do that either. Right. So we have adjacent, so both of them, since both of them starting at O, so that means they share the vertex O, so the sides are adjacent. Right, cross product OP cross OQ. Actually on this one it doesn't matter, we just take two of them cross each other, because after all the area is also positive, so we have to put the absolute values into it. And by absolute values I mean the magnitude. But the cross product here, just do the cross product in general. Doesn't matter which one cross the other one. So 2, 3, and 4. 3, 2, and 0. right? So that will be 3, 4, 2 and 0 I minus 2, 4, 3 and 0 in J plus 2, 3, 3, 2 K. Right. So cross that. That is negative 8 I 0 minus 12 with another minus plus 12J four minus 9 is negative 5K. So we have the cross product, and then we just take the magnitude. So we have negative 8 square, 12 square, negative 5 square. $233. Forget the square root. Right. So that is the area of the parallelogram. We need to cut that in half for the area of a triangle. So we say area of triangle OPQ equal to 1/2 OP cross OQ 1/2 square root of 233. So yeah, so just like that, simple enough, right? Next, we have an example here. Find the area of the parallelogram whose vertices is this. Usually, it should work the way that P, Q, R, S, or whatever it is, the orientation will be some certain clockwise or counterclockwise. What I mean is, when the problem P, Q, R, S, it should be P, Q, R, S like this, and not P, Q, R, S. So direction kind of one direction. It's not zigzag like that. Right. We can also check. Let's find the vector PQ. Our vector PQ is Q minus P. Q 2, 2, 3 minus P 1, 1, 1. When we subtract, we will have a vector, so I use the vector notation of the bracket 1, 1, and 2. So we have vector PQ. Now, if we want to make sure that it is actually a parallelogram and the orientation, so kind of sketch. I say PQRS in this order. If we have the vector PQ, the vector that is equal to it will be SR. So just find the vector SR and see if they actually parallel. Vector SR is going to be R minus S, R minus S. 1, 1, and 2. Yes, in this, the vectors are equal, so they are a parallelogram, which is good. Not only they parallel, but the fact that they parallel and have the same magnitude make it a parallelogram. It cannot just parallel. In that case, this does not form a parallelogram, right? But this one does, if they have the same length. So opposite sides are parallel and equal length, but we cannot cross those two. Cross those two give us 0. So let's cross the adjacent vector like PQ and PS. PS is S minus P. S is 0, 2, and 1. Minus P, 1, 1, and 1. So that will be negative 1, 1, negative 1, 1, and 0. And then the area of parallelogram. First we do the cross product and then we find the magnitude. Of course we can find the magnitudes and then we times the sine of the angle between them. That works out just fine. But like I said, just do the cross product first. PQ cross PS adjacent sine. I, J, K. It doesn't matter PQ cross PS or PS cross PQ, because after that we take the magnitude. So if we have a positive or negative, it doesn't matter, because after all we take the magnitude. So whether it pointed up or pointed down, as long as the magnitudes are the same, we are good. So PQ 1, 1, and 2. PS negative 1, 1, and 0. So still want to do that. 1, 2, 1, 0. I minus 1, 2, negative 1, 0, J. 1, 1, negative 1, and 1, K. So that gives us 2, actually negative 2, I, 0, that is negative, but this direction is negative 2, so it's actually, if you write down, it will be 1 times 0, subtract 2 times negative 1, J, plus 1 times 1, and minus that, which is K. So it's negative 2I, and that is 0, that's 2, negative J, negative 2J, and then 1, then so that's 2K. And then the area of parallelogram, so we say area of parallelogram. PQRS equal to the magnitudes of PQ cross PS. So negative 2 square plus negative 2 square plus 2 square. So all from 4, 4, 4, so that's 12, square root of 12 is the area of the parallelogram. Once again, we can do a lot of like PQ cross PS or SP cross SV, it doesn't matter. Or we can do PQ cross SP, it doesn't matter. As long as two adjacent vector, direction doesn't really matter. But have to be adjacent vectors. Right, now we have an application of a cross product, what we call a torque. So twisting generates a force, so we still have a force acting at a distance, so we still have two things like a force and a distance, but not a dot product. This is a cross product. The direction of the torque vector is determined by orthogonal to both F and R. The torque or the twisting effect produces a force orthogonal or given by this. So the torque is that is the Greek tau, the Greek letter T. As opposed, so just like that, cross product. And of course, if we want to, we can say this is equal to, yeah, I'll not even worry about that. Right, next, we have an example. So the torque in terms of unit, so torque equal to R cross F. Both of them are vector. So R is the distance, the unit is Newton. I got them backward. Distance, the unit is meter. Force, the unit is Newton. Newton meter is also joule. Right. Suppose you apply a force of 20 Newton to a range attack to a bomb. So it's like this. In direction perpendicular to the bomb. Which produce more torque? First you apply that at 60-degree angle. So it is like this. So apply the force in this direction. And at the point that is 0.15 meter away from it. So we try to pull in that direction. The torque is of course determined by the right hand rule. It's going to go up in that direction. Right. By the way, vector has no location, so why do we move the F, vector F in here? So this is the vector F for the force. And we have the vector here, R. And then we have the angle here. Since this is 60 degrees, that is 60 degrees as well. And the right hand rule, that's say pointing up. Right. So either we do that or we're going to apply the force. That is 20 Newton, still 20 Newton, but 0.25 meter away from it. So we pull in that direction. Still, we can move the vector F in that case. And we have the vector R. And that is 135 degrees as well. So by right hand rule, that also point up. Right. So on this one, if we actually try to find the torque using the cross product and try the vector component and do the cross product, that would be a bit much. We prefer to just find the magnitude. So we've said the magnitude of the torque. Just that, which is R and then F. Magnitude of R times magnitude of F times the sine in between them. In this case, we have sine of 60 degrees. Right. As mentioned before, whatever we put here should be positive. To ensure that we have the magnitude which is positive. Right, then we have everything. 0.15 meter. We can even put the unit there. The force 20 Newton. Of course, 20 times 1, that would be 3 joules. Simple enough. if I do it correctly. Sine of 60 degrees. Right. Let's get that small number. 0.15 times 2 times 20, sorry, times sine of 60 is 2.59 joules. Right, and then we do the same thing here. The total magnitude of it equal to R cross F, which is the magnitude of R times the magnitude of F times the angle. This time the angle is 135 degrees. So R 0.25 the force, magnitude of force 20 Newton, and sine of 135 degrees. So, by the way, yeah, this is in degree mode. 0.25 times 20 times sine of 135. So this is 3.54 joules. So this one has more torque than that because the magnitude is bigger. Both of them point in the same direction. Right. Next, we do the comparison between the dot product and cross product to conclude this section. Right. So cross product and dot product. What do they have in common? Actually, I don't think they have anything in common. Right. So what they have in difference? Contrast. Right. The dot product. So dot product is, first of all, work for any dimension, vector in any dimension. BR2, R3, any dimension. This only work for vectors in R3 principle. Next, the dot product is a scalar. Meaning it's a number. Cross product is the vector. That's the main difference there. What else? Dot product. U cross V, U dot V is the same as V dot U. So they commutative. And where cross product, U cross V is equal to opposite of V cross U. Next, the dot product is equal to the product of the magnitude times the cosine of the angle in between them. Could be positive, could be negative. So this dot product could be negative. However, in the equivalent, in here, we have to throw in the absolute values. We have to throw in the magnitude. So when we say the angle between them, whatever it is, it has to be positive. So this one has no magnitude, this one has. a magnitude. Right, what else? Right, because this one has no direction, so it's nothing there. But this one has a direction. Direction is determined by the right hand rule. And of course, dot product is a scalar. It has no direction. Right, what else? This of course gives us the area of the parallelogram, of course, but we don't have anything kind of to compare to the other side. Right, in terms of application though, application for the dot product is work either r dot f or f dot r, it doesn't matter. But the torque is a vector r cross f. We cannot switch r and f, because if we switch, let's throw in the negative sign. Right, and then of course we can do the orthogonal projection here, and then the area parallelogram there. Angle between two vectors, it will be better to use this formula than the other one. Right, so that pretty much contrast between the dot product and the cross product. Right, so it's not that big, but just be mindful with this one. The dot product doesn't have the magnitudes, therefore the angle could be positive, could be negative. It doesn't matter though, right? But if the angle is more than 90 degrees, cosine of anything more than 90 degrees, it is going to be negative. So the dot product, the angle between them, we can put any angle, positive or negative here. Still work, but it have to be between 0 and pi, or I guess it's between 0 and 2 pi. Still fine. Any angle, still fine. But if we find the angle, we just take the cosine inverse, and that whatever we have the cosine inverse is the angle between the vectors. Right. So angle here, to do this kind of easy, but when we do here, make sure the angle is positive because we have the magnitude. Right. And then the dot product, we can just take two vectors, do the dot product. The cross product, we have to know which one go first, which one second, because that's different. And finally, just the notation. You see the work here, that is not a vector, but the torque here, it is a vector. So cross product is a vector, make sure it is a vector, and then so we write the proper notation for a vector. And the dot product is a scalar, so it's just a number. Alright, so with that I stop section 13.4 here. See you in another video on Calculus 3. Thank you for watching.